Okay, so let's get going. So today we're going to talk about damping. We've already had one lecture where we talked about the logarithmic decrement, where we talked about free vibration damping and the decay that we had in our free vibration system. So today we're going to talk about some of the other forms of damping that we see in our vibration systems. So most of the damping that we've looked at so far, we've had a damping force F is equal to a constant c times a velocity x dot. Okay? And we've been calling that viscous damping, haven't we? Okay, and when we've been drawing little schematic diagrams, we've had something like this, haven't we? Okay, to relate. So this little element is supposed to relate some fluid inside a container or tube, and then there's some plunger which is being pressed into the fluid. Okay, and it's the resistance of the fluid which gives us this damping. So we can note that the power dissipated by a damper power is the rate of change that work is being done. So it's sometimes written like this: d by dt of w, where w is work, and that's equal to force times velocity. So in this case the force is c times x dot, and if we multiply that by velocity, which is x dot, we get cx dot squared. For harmonic motions, okay, so if we've got a harmonic motion, which is the type of motions we've been discussing throughout this course, then we'll have something like that. X is equal to big X times a sine wave. And inside the sine wave you've got omega t minus phi. So omega is the forcing frequency, phi is the phase lag. So if we take one cycle of motion, so we're periodically forcing it with this sine wave, right, we'll get a energy dissipated which can be written as this: pi c omega x squared. So I'm not going to derive this, but I'm just going to give you a reference here to where you can find this if you want to. Okay, so it's this book by Merovich called Fundamentals of Vibration, and you can find that derivation on page 137 if you need it. So these are some basic facts around viscous damping. So there's another concept called hysteretic damping. So it would be it's quite reasonable to say, well, why are we bothering to look at this hysteretic damping? Okay, so viscous damping is relatively easy. We know that this constant times a velocity. Well, the issue is that viscous damping is easy, but it doesn't always reflect the real behaviour of the sort of physics of the systems that we're considering. Okay, so hysteretic damping is a way of trying to get closer to the physics for a lot of the systems that we encounter. So, and the reason, and the best way to model it, there's several ways to model it, but the simplest way is a combination of spring and damper. So in this case, the force would be equal to Cx dot plus Kx. And you may say, well, that's just a spring and a damper. And you're right, it's just a spring and a damper, but we can adjust the phasing in these relationships to give us what's called a hysteresis loop. Okay, so the reason this is called hysteretic damping is because we get a hysteresis loop, and I'm sure you've seen that in some of your other lectures. Okay, so hysteresis loop looks like this. Okay, so although this looks like it is just a spring and a damper, you're absolutely right. What we can do is we can design it in such a way that it represents this kind of loop behavior, okay, which is more realistic to the physics that we see in a lot of systems. So again, we're going to look at harmonic motion. So, and we're going to make simple assumptions to start with. So if we just assume it's a sine wave and ignore the phase for now. Okay, so we just assume that to start with. So we can substitute those into the expression for F. And then we're going to, what we're trying to do now is we're trying to get something which develops this loop idea. Okay, so we're going to do a little bit of manipulation. Okay, so what we're going to show is that if we have something like this, okay, so cos squared plus sine squared equals 1, doesn't it? Okay, so we can write this down. So hopefully we can convince you that that's also acceptable. This bit here is just x squared, isn't it? Little x. Okay, so big X squared sine squared is just small x squared. So we can write down this down. And in a minute I'll show you a slide. But basically what this is showing is that if you have a straight line relationship between force and velocity, that's like a constant times x, isn't it? I think this diagram should be in x, not in... Let's draw a new diagram. That one's in x dot. So this straight line can be kx, can't it? Yep. In here. So I rearrange this. So I move this term to the right hand side. So I get big X squared minus x squared sine squared. Then I square rooted both sides. Right, so on the left hand side I get x times cos equals plus or minus square root of the right hand side. Oh, it's not. No, that's not divided by. What I said was this term is equal to little x squared. Okay, so this term here. So this is kx. Okay, so this f now is equal to plus kx plus or minus this square rooted term. Okay, so for any point here x, we've got points above and points below. Okay, like that, plus or minus. And what that means is that we end up creating this loop. Okay, so yeah, go ahead. It's not supposed to be a circle. I'll show you an example in a minute. It's usually it's an ellipse. This definition is actually an ellipse. But in reality, actually, we see in physics things that aren't ellipses primarily. But this is an approximation to try and capture that behavior. So what we say is this gives an approximate hysteresis loop. And as I say, the main point of all of this is to try and capture this physical behavior that we observe in practice. So we can make a link between viscous and hysteresis So we can define a new variable h as equal to omega times c. So then the energy dissipated delta W would be equal to pi h big X squared and the force would be equal to h over omega x dot plus kx It's typical now to use exponentials. So small x is equal to big X e to the j omega t. So f is equal to So you can see in some ways why this new definition of h was chosen, because on the first term now the omegas were going to cancel out. Okay. So we're going to end up with something like jh plus k and this is usually manipulated a little bit further. Okay, so these terms are normally swapped round, and we take a factor of k outside the bracket. So we have k outside, and we swap them round, so the first term would be 1, and the second term is now called j times beta, so we introduce a new parameter. So beta is a new parameter which is called the loss factor, and it's equal to h over k. And this whole term, k times the bracket 1 plus j beta, is called complex stiffness. So we can include this in our single degree of freedom models. Okay, so we can write it like this if we want to. So we can have a single degree of freedom equation, mx double dot, and C equivalent x dot kx equals f, and C equivalent is k beta over omega. Or we can have mx double dot plus k 1 plus j beta x equals f. So that's hysteretic damping. As I say, it's there to try and take account of the physics, but as you've seen, it's a little bit more complicated than viscous damping. So another concept which we need to think about, again the physical one, is friction damping. And usually people call it Coulomb damping. So, named after Coulomb, because apparently he's the person who devised this particular type of model for friction. Okay, there's many different ways of modelling friction. This one's Coulomb's model. People sometimes talk about dry friction as well. So, and this is arguably the simplest model. Okay, so you can think about it like a block with mass m that's just resting on a surface. Okay. So the block's just sitting there doing nothing. Of course, by doing that, it's producing a normal force downwards, n, which is equal to mass times gravity. Okay, and so there's a reaction force underneath as well, isn't there? So if we try and slide this block along the surface with a velocity x dot, okay, so if we try and push it, then it resists the motion with a friction force mu times n. Which is the normal way that this is written. So mu is a special parameter. It's called the coefficient of friction. Okay, so that's easy to understand, isn't it? So here's just a little thing to think about. So if I've got the same block M, but I turn it on its side, okay. So this is trying to represent the same block. It's not a square block; it's a rectangular block, okay. Then the friction force is exactly the same, isn't it, right? Because M produces a downward force of m times g, regardless of whether it's laying on its side or it's standing on its end. Okay, so if I try and move either of these blocks in a velocity, then I get friction force of mu times n. Is that correct? So mu n. So that's right, isn't it? So the fact that this area could be double this area, we don't care about that, do we? Does anybody care about it? That's not what the textbooks say. you could be right, but the textbooks say that it's just dependent on the normal force. Okay, so probably you've seen friction laws like this before, right? So the textbooks in mechanics books will say the friction force depends on the normal force. Okay, so that the only way that that can happen is if the area here is exactly the same as the area here, right? Okay, and the only way that can happen is if we look at under a microscope what's happening. So under the microscope, the surfaces look like asperities being pressed together, don't they? They don't look like flat planes, because under a microscope these surfaces are actually quite rough. So if we imagine that they're like this, okay, in the one that's got the bigger gross area, right, the pressure will be less, right? So there'll be less; these asperities will be less squeezed together, won't they? Okay. Whereas in the one where there's a smaller overall area, there'll be more pressure. Right, so there'll be more asperities being squeezed. So if you add up all the tiny little bits of actual contact area, like this little bit here and this little bit here and so on, okay, the actual contact area has to be the same if this theory is to be believed. Okay, and that's how people argue it. They say that if you look on a microscopic level, then the actual contact, the interface of these interlocking asperities is the same, and as a result, we can we're good to go. But you need to be careful about that, because it only works if the materials are the same, right? Because if this material pressing here and this material pressing here are relatively similar, okay, like steel on steel or something like that, then that works reasonably well, doesn't it? But if it's a bicycle tyre on the road, okay, a bicycle tyre is soft and the road is relatively hard, okay, then the whole thing breaks down, and that's why Formula 1 cars don't have very narrow bicycle wheels on. Well, it's one of the reasons. There's several other reasons, and that's because they're trying to generate friction in an environment where the materials are very, very different, okay, between the two different surfaces. This kind of a mechanics assumption only works if the materials are similar, and even then it breaks down for some other things. Okay, so that's just a little aside. Let's have a look at the Coulomb model. Oops. So the Coulomb model is the simplest way of thinking about these frictional things. Okay. And if we plot the friction force against the velocity, then typically what we do is we have mu times n here minus mu times n here. And the Coulomb model essentially assumes that that's just a constant value regardless of the velocity. Okay. Now, again, we know that that's not quite true when we look at the physics, but it's not a bad approximation. If we look at the physics, we actually get something which drops down here and goes up to a peak, and then kind of goes down like that, and then tends to go off like that. Okay, so we have a more complicated kind of real physical environment, but this sort of straight line relationship is actually not too bad at capturing some of those key kinds of behaviors. And we can represent that behavior simply as F, this friction force, is equal to minus sine x dot mu n. So sine of a function, when you see sine of that, it just means plus or minus 1. Okay, so if x dot is positive, it's 1. If it's negative, it's minus 1. Okay, so sine x dot equals 1 when x dot is positive, minus 1. Is that okay? And this is a squiggle, so I've just crossed something out there. Sorry about that. Sometimes written as signum function, like SGN. Have you seen that before? Okay, so it means the same thing, either sine or SGN. Yep. The signum function is just as defined here, look. What's that? Plus or minus 1? So, for our single degree of freedom vibration system, what does this mean? Well, it means that we have a system which, again, this is all very simple and conceptual, but we can have a system that's designed like this. Okay, so a mass and a spring, and the mass is assumed to be a block which is going to slide on the surface. Okay, and that's going to provide the frictional damping. So there's our single degree of freedom, x. This time is a horizontal translation. And the equation of motion looks like this. So what we have is we have mx double dot, so we have the inertia term mx double dot to start with. Then we have the damping term, which in this case is a frictional term, sine of x dot times mu times n. And then we have the spring stiffness term, the restoring force kx. And then the right hand side is equal to 0. Okay? So let's have a quick look at a couple of pictures now, which hopefully explain some of these concepts. So just going back, before we talk about friction, let's just go back and look at the hysteresis loop. So in the lecture note slides, you can find this diagram, and here you can see how this ellipse is being created by these two terms. Okay, the red line being the kx term, which is like just a linear part, and then the plus or minus, the blue part, which creates the upper and lower parts of the ellipse. Okay, and then here you can see. So we were saying, you know, what do these things look like in reality? Well, the left-hand one is quite similar to a lot of hysteresis loops you find in reality, okay, which is not the same as the ellipse. So the ellipse is an approximation, but it does at least get closer than a straight line. So the alternative is just to have a straight line, okay. So here we go on to friction. So you can see what we've covered in the Coulomb model. So, but this is the important diagram for friction, right? Because this friction oscillator is just like a free vibration oscillator, okay? So if we set it going, it's just going to dissipate energy by sliding backwards and forwards on this surface. But it's going to do it in a fundamentally slightly different way from the viscous one, okay? And if you look at the way the curves go in terms of the envelope, they're straight lines, okay? So you can see that there's a straight line above and a straight line below, whereas before they were like exponential curves, weren't they? Okay, so for viscous dampers they were exponential. And if you look in a lot of exam papers, it often asks you the question. It shows you a decay curve, and it says what type of damping is it. Right? It's easy. If it's a straight line, it's friction, and if it's an exponential, it's a viscous. Okay. And so if you look back in the past papers, in fact, people were asking me if I could release the past papers in time for Easter, so I've done that already. Okay, so you can look back now over the last however many years of past papers we got on mole. You'll find quite often that question is asked, and it's asked because it's easy visually to see. If you know your stuff, you can look at it and very easily tell the answer, can't you? Okay? So that's it. I'll see you all on Wednesday.